And then for today, we are still working with piecewise functions, but more specific types of piecewise functions called step functions and then absolute value functions. So I believe both of these, well, I know they're part of Algebra 1. So again, if they seem familiar, you may have seen them in Algebra 1. If they don't, I teach them as if you haven't seen them anyway. So just because they're brief in Algebra 1, they're kind of just introduced for the first time and they're not really covered in depth. So the first two examples deal with step functions. And what it says at the top, so unlike a piecewise defined function like we did on Thursday, where the function itself you saw you had 2 pieces or 3 pieces, a piecewise linear function is going to contain a single expression. So you're not, like I said, you're not going to see, oh, this graph is going to have 2 pieces, this graph is going to have 3. You're going to see just an expression, and you're going to have to know the graph is piecewise and what the graph should look like. So a common piecewise linear function is called the step function, and the graph of a step function is going to consist of line segments. So it's called a step function because the graph is going to look like steps. There is a graph off to the side here that you can see. This graph, though, specifically is the greatest integer function. So the greatest integer function, which is written as f of x equals, and then it's x inside of a double bracket. This is one kind of step function. I'd say it's the most common kind of step function you're going to see. And that symbol, the x value with the double brackets, this means that you are finding the greatest integer that is less than or equal to x. So that's worded a little bit strangely, in my opinion. But what it means, I have 3 examples so you can understand what it means. So if I see 3.25 inside of those double brackets, I'm finding the greatest integer that's less than or equal to 3.25. So I'm going to explain 2 ways to think about this. One way is think about what 2 integers this number is in between. So 3.25 is in between 3 and 4. So you are then choosing the integer that is less than this number. So it would be 3. So the greatest integer less than or equal to 3.25 is 3. Another way to think of it is you're always rounding the number inside of those double brackets. You're rounding it down, always. No matter what the decimal place is, it doesn't follow the normal rules where if it's 4 or below, you round it down, 5 or above, you round it up. You always round it down. So if we look at negative 4.6 inside of the double bracket, so the greatest integer less than or equal to negative 4.6, what do you think that would be? If you follow the same rule we did for the first one. Grace? Wouldn't be negative 4, Allie? Negative 5, yes. So negatives are a little trickier, so it is between negative 5 and negative 4, and remember negative 5 is lower, so this would be equal to negative 5. And then for the next one, so it does say the greatest integer less than or equal to the number inside. So if the number inside is an integer, it's just equal to itself. So the last one would just be equal to 2. All right, so then we'll be going through in example 1, working with that greatest integer notation. But this is what the graph, this would be called the parent graph of the greatest integer function, because the function is just the greatest integer less than or equal to x, whereas if you just look at the function we have in example 1, there's things happening to that function. The negative 2 and the minus 5 are changing that function a little bit. But this would be called the parent function. Just take a look at what it looks like. Again, it looks like steps. There's dots, there's circles, there's short little line segments. So our graph is going to resemble this, but obviously as you introduce other numbers in the function, it's going to transform it. So it's not going to look the exact same. But for this parent function, the domain and the range, domain will always be all real numbers. For every greatest integer function, it will always be all real numbers because x can be anything, can be an integer, can be a decimal. The range, though, this is what's going to vary. The range of the parent function is not all real numbers. All of these short line segments are only at integer values of y. So y is never going to be a decimal. So the range is just all integers. But like I said, the range is what's going to vary between examples because sometimes your line segments might not be at every single integer. It might skip over some integers. So then you have to decide what the range really is. So we're going to take a look at example 1, graphing one of these. We have f of x equals -2 times the greatest integer less than or equal to x minus 5. And then we'll identify the domain and the range. And the way I typically go about graphing these, I make a table. And I'm only using the table to figure out a pattern. So as we're making the table, kind of have that in your mind, you're looking for a pattern. I can substitute anything I want to in for x. I typically substitute the same x values in every single time for these. I do some integers and then some decimals. So I will typically substitute in 0, and then I substitute in 0.25, 0.5. I could do 0.75, but I typically just do a couple of decimals in between 0 and 1, and then I substitute in 1. And then again, a couple of decimals, so 1.25, 1.5, and then 2. And I could continue that, but this is usually enough for me to see a pattern in the y values. And once I know the pattern, I can fill in the rest of the graph. So now to actually find the y values for these x values, and you're going to see some y values repeat. So I'm substituting in 0 for x. So when x is 0, my y value is going to be calculated with -2 times the greatest integer less than or equal to. And if I put 0 in for x, I have 0 minus 5, which is just -5. So then make sure that you're evaluating the greatest integer less than or equal to this number before you multiply by -2. So since -5 is an integer, this is just going to be -2 times -5, which is +10. So when x is 0, the y value is +10. And then if I do that same thing when x is 0.25, I'll have -2 times the greatest integer less than or equal to. And if I put 0.25 in for x, 0.25 minus 5 is going to be -4.75. So before I multiply by -2, I need the greatest integer less than or equal to -4.75. So what integer would that be? -5 still, because again it's rounding down. So I'd have -2 times -5 still, which is still +10. So my y value didn't change even though my x value did. Okay, now 0.5, same thing, -2 times the greatest integer less than or equal to. If x is 0.5, I have 0.5 minus 5, and that's -4.5. So I need to evaluate the greatest integer less than or equal to -4.5 first. What integer would that be? If I round -4.5 down, what integer will it be at? -5 still. So -2 times -5, so that's still +10. And then if I substitute in 1, so now I have -2 times the greatest integer less than or equal to. 1 minus 5 is -4. And now -4 is an integer, so that'll just be -4. So now it's -2 times -4, which is +8. So my y value changed finally. So notice whatever decimal I would have plugged in between 0 and 1, even if I would have plugged in 0.75, even 0.8 or 0.9, all of those y values would have been 10. When x changes to 1, the next integer, the y value changes to 8. So then this is where I say look for a pattern. So if x is 1.25, what do you think the y value is going to be? 8. It's going to follow that same pattern because the greatest integer is still going to be rounding to that -4. If x is 1.5, what will the y value be? Well, the y value will come out to be 8. Yeah, the integer would come out to be -4 again. If x is 2, what would the y value be? 6. So every time x changes to the next integer, the y value is changing by going down by 2. So look for that pattern. So now to graph this, and again, notice it's helpful if you have in your mind a picture of or an idea of what it should look like. So it's going to be steps, short line segments, a dot at one end, a circle at the other. So this is how you can make the graph. So I'm going to plot my first point is 0, 10. That should be a dot. Okay, and then I would also have points, and I don't really need to plot these, but so you get the idea, if I went to 0.25 and then 10, and then 0.5 and 10, so anywhere between the x values 0 and 1, all of those y values are 10, and that's what creates that short little line segment. So from 0 to 10, I would draw a short little line segment over to where the x value is 1, and at the very end of that, I would put an open circle, because when x is 1, the y value changes to 8. So at 1, 8 would be my next dot. So notice at that x value 1, you're going to have both a circle and a dot on separate line segments. And then I continue that pattern. So at 1, 8, I draw a line segment over to where x is 2, put a circle, because at the x value 2, the y value is jumping down to 6. That's where my next dot is. Okay, that's all I have in my table, but I should still then continue this for the rest of the coordinate plane that I have left in both directions. So I can't go anywhere to the left because that'll be up and off of the graph, but I can continue this down and to the right. So starting at 2, 6, I draw a line segment over to where x is 3 and put a circle. And then when x is 3, what's the new y value going to change to? Where would my next dot be? What y value? At 4. So at 3, 4, I'd put my next dot. And then at 3, 4, draw a line segment over with an open circle. And then at 4, my y value is going to jump down to 2. At 4, 2, line segment over with a circle. And at 5, my y value jumps down to 0. Draw a line segment over, put a circle. At 6, the y value jumps down to -2. And then I just continue that pattern. And although, I could put a point at 10, -10, I could kind of finish that line segment if you wanted to, even though it's off the graph, but that's as much as would fit on this coordinate plane. So if I could have drawn the other direction, if it wouldn't have been off the graph, I should do that. So questions at this point with making the table, making the graph? Okay. Then domain and range. Like I said, domain will always be all real numbers because, again, x can be any number, integers or decimals. The range, though, you can look at your graph or you can even look at your table. The range of that parent function was every single integer. That will not be the range for this one because we started at the y value 10 and then we jumped down to 8. So that y value 9 isn't part of the range. Then we jumped down to 6. Anybody know how we could classify the range for this one? Say that again. Yes, even integers. So I could say the range is all even integers. Would be one way to say it. Another way to say it, I could say, and I'll just write this above, I could say integer multiples of 2. And why I'm writing that down is, say your line segments or your y values were skipping every 3. We can't obviously say even or odd if it's skipping every 3, but we could say integer multiples of 3. Or if it's skipping every 4, integer multiples of 4. So that's just another way to say it if it isn't every 2 with even or odd. Any questions with example 1? All right. Then example 2. So this is more of an application with a step function. And ultimately, the question is just asking you to make a graph. So thinking ahead to the practice you will be doing, you don't have to necessarily fill in the table. The table is there as a guide, and we'll fill in the table with this one. But ultimately, you're making a graph. So this is a scenario in which if the situation was represented on a graph, it would be a step function. So we have an automotive repair center charges $50 for any part of the first hour of labor and $35 for any part of each additional hour. So then it says draw a graph that represents the situation. So before I start filling in the table, I just want to understand what information I'm given, understand what this is saying. So say I take my car to this automotive repair center and say that it has been there for 0 minutes. Will they charge you anything? If they haven't even started working on your car, are you charged? No. So 0 minutes, there's no charge yet. Say my car has been there for 1 minute. How much will they charge you? $50. So it's $50 for any part of the first hour. So 1 minute, you're charged $50. What if your car is there for 30 minutes? $50. What if your car is there for 1 hour? $50. Okay, so anywhere from even 1 second up to 1 hour, you're charged $50. Say now your car's been there for an hour and 1 minute. How much will you be charged? This is a 5 here, sorry. Yeah, the next cost will be $85. So it's the 50 for the first hour, plus now an additional 35 because you're going into the second hour of labor. And that trend will continue. So if I were to put this information into a table, I'm going to have X represent the time in hours, and then Y is going to be the cost or that charge in dollars. So this is why I included the 0 minutes. So anywhere from 0 minutes to 1 hour, that charges $50. However, at 0 minutes, I'm not paying $50, but at 1 hour, I am. So a way to write that is my first charge is going to be $50. I'm going to write the X values as an interval from 0 to 1, 0 to 1 hours. And I'll write it down and then explain it. So I have that compound inequality, 0 is less than X is less than or equal to 1. So I do not include an equal sign with the 0 because, again, at 0 minutes, I'm not being charged. But at 1 hour, I am being charged the 50, so the 1 is included there. Okay, my next charge then is jumping up by $35, so that's $85. And that's going to be anywhere from 1 to 2 hours. Again, 1 will not be included. but 2 hours will be. So if my car is there for exactly 2 hours, I'm still paying $85. The 1 is not, though. At 1 hour, I'm paying $50, but just past 1 hour, I'm now paying the $85. What will the next cost be after $85? It'll jump up to $120, and that'll be from X values anywhere between 2 and 3 hours. 2 is not included, but 3 is. The next cost, if I add another $35, would be $155, and that would be anywhere from 3 to 4 hours. 3 is not included, but 4 is. And then adding $35 again would be $190, and that would be anywhere from 4 to 5 hours. 4 is not included, 5 is. So this table, like I said, it's not a necessity to fill it in, but now it gives me an idea of how I should scale my graph to fit more than just one line segment on there. So when you graph these, you should see more than just one piece of your graph. If you only see one piece, you should scale it differently. So I'm going to just draw in the X and the Y axis and then write in my scales for both X and Y. And this again is 10 by 10. So my X values is just the number of hours. I can just count that by ones. And then looking at my table, at the very least, I want to fit the Y values 50 through 190. And I have 10 spaces. What could I count by? Okay, I could make a break in the graph to start at 50 and then count by 35, since that's how my Y values are changing anyway. That's perfectly fine. So 85, 120, 155, 190, and then I would have 125, 160, nope, 225, 260, sorry, 295, 330, 365. And then I can actually fit in more of my graph than even what's in the table. So now with these types of scenarios, if you take a look back at the graph we had just made and even the parent graph, with your line segment, it was always a dot and then the line segment and then a circle. For these, sometimes the dot and the circle switch, and you have to determine where it makes sense to have your dot and your circle. So to explain that, if you take a look at these inequalities, hopefully it makes sense. When I'm at 0.50, at 0 hours, I'm not paying $50, so I should have a circle there. Because if I have a dot, that means at 0 hours, I'm being charged $50. And my line segment then goes over to 1. At 1 hour, I am paying $50, so I should have my dot there. So here the circle and the dot are switching from the last example we did. And then still at the X value 1, now my cost is jumping up to 85. So at 185, I would have a circle, line segment over to the X value 2, and I would have a dot because at 2 hours I am paying 85. And then I would follow the pattern. So now jump up to 120 with a circle, line segment over, dot. And then I can even continue past what was on my table based on how we scaled this, because that pattern is just going to continue. So there are a lot of scenarios where if they were graphed to represent what's going on, you'd have a step function. This is just one of those. I know cell phone plans have changed a lot, but it used to be, you know, kind of for a range of minutes or data, you're charged the same amount, and then it'll jump up once you pass that point. So a lot of cell phone plans could probably be represented with step functions as well. Are there questions on number 2? Okay, those are the examples I have for step functions. Absolute value functions are next, and I'm just going to go through example 3 with you. I have 2 examples. That was if we had time, I'd rather give you at least a little bit of time to start your assignment. So absolute value graphs, and these are, in my opinion, easier to graph. So these are piecewise functions, and we'll talk about why. But make sure absolute value functions are functions that contain an algebraic expression with an absolute value symbol, so you will see absolute value bars. So just like I said on the previous 2 examples, if you see the double brackets, think or know that's a step function and picture what the graph should look like. It should be a series of steps. If you know that ahead of time and can picture it, it's easier to understand what to do in order to graph it. When you see absolute value bars in a function, the graph should be a V. So knowing the end result, it should make a V, might help you, first of all, make sure when you graph it that it is a V. And then if it isn't, kind of reevaluate, but know ahead of time or kind of trigger how you should graph it. What is underneath here, so this is the parent graph of the absolute value of x. This shows why it's piecewise, so it's made up of 3 different pieces. I'm not going to focus too much on those because we don't really need to focus on them. Has a V shape. This is the domain and the range for the parent graph. The domain will always be all real numbers. The range might change depending on if your graph is shifted around. It is all non-negative real numbers. Another way to look at that is note where the corner of the V is. That's the vertex. And that is at the y value 0. And the V is opening up, so it's all y values greater than that. So it would be greater, or y is greater than or equal to 0 for the parent function. That might change, again, depending on if your graph is shifted around. It also gives you the x and y intercept of the parent function and then where it's not defined. I won't focus too much on those because we're mainly focusing on graphing it. Are we getting the right shape? And then finding the domain and the range. So for example 3, we're going to graph f of x equals the absolute value of 2x and then minus 4 and identify domain and range. I also graph these by making a table. But the table setup is different from step functions. So again, I see absolute value bars. I should think end result, my graph should be a V. When I make my table, I can plug in anything I want to for x. I like to know ahead of time where the vertex of my absolute value graph is going to be, and there's a way to find it. So to find where your vertex is going to be, you take what is inside the absolute value bars, and only what's inside the absolute value bars, so that would be 2x in this case, and you set it equal to 0. You always set it equal to 0. And then you solve this for x, and that'll give you the x value where your vertex is. So if I solve this for x, divide each side by 2, I get x is 0. So at the x value 0, that's where my vertex is going to be. And then I can choose a couple of x values on either side. So I might choose -1, -2, and then +1, +2. Because otherwise, if you're just picking x values, you might not get your vertex value in there, and then it'll appear like you just have a line, which it shouldn't just be a line. So knowing where that vertex is helpful. And now I just substitute these in. Make sure when you substitute them in that you are taking the absolute value. So for example, if I substitute in -2, I have 2 times -2 is -4, and then I have to take the absolute value of -4, which is +4, and then subtract 4, so the y value is 0. If you do not take the absolute value, your graph is going to come out to be just a line. So that's where I'm saying if you know it should be a V, that can be helpful so that if you don't just leave it as a line. If x is negative 1, 2 times negative 1 is negative 2. The absolute value is positive 2. Minus 4 is negative 2. If x is 0, 2 times 0 is 0. The absolute value is still 0. Minus 4 is negative 4. If x is 1, 2 times 1 is 2. The absolute value is 2. Minus 4 is negative 2. And then if x is 2, 2 times 2 is 4. The absolute value is 4. Minus 4 is 0. So another thing you should see is on either side of your vertex, the y values are the same. And that's what makes the v. So if you don't see that, then perhaps you forgot to take the absolute value or you didn't find the vertex correctly. Just some things to check. So now if I graph these points, I should see they do make a V, and I can draw that in. Sometimes your V will open down. So as long as when you're substituting your values in, you're following order of operations, taking absolute value, you should be good. Domain is always all real numbers. X can be anything. Ideas on what the range is for this one. It's different from the parent graph. And if it helps, kind of look back here, the vertex was at the y value 0. It was opening up. All y values are greater than or equal to 0 was the range for that one. So what about for example 3? Allie? Yes. Vertex is at the y value negative 4 and it's opening up, so all the y values are greater than or equal to that value. And if it opened down, it would just be less than or equal to.